go ahead and get started.
Cool. So this is chapter 8, efficient hardware. I sort of went way off the deep end compared to the book, just because this is something I am a little passionate about and know a little bit about. So I think we're gonna have some fun. We are going to learn what a byte is, how the CPU, RAM, hard drive, and solid state drives, which are memory and storage, contribute to overall speed. Some of the differences between 32 and 64-bit, and the ways you can, if you have to use 32-bit for something, the ways you can try and avoid it as much as possible. And then there's like a very clickbaity what you can do so you don't have to worry about any of this. So jumping in, what is a byte? So computers only know on or off, so binary ones or zeros, and that at the most basic level is how everything is represented. And so computers early on, if we wanted to see human readable text, people came up with 128 their ASCII characters. I forget what ASCII stands for, but it was all of the upper and lowercase letters of the Latin alphabet with some numbers and special characters thrown in. And there are 128 of them because that is 2 to the 7th power. But then later on, thank you, John, the American Standard Code for Information Interchange. And later on, an 8th-bit was added as computers moved more towards using powers of 2 for everything, because 8 is 2 to the 3. So then we have 8 bits to make a byte, which is a whole ASCII character. And in the book, they link to a very heated Stack Overflow discussion about whether or not ASCII is supposed to have 7 characters or 8. But in a pure conversion world, 100 characters would be 100 bytes, which would be 800 bits. And this is often not so straightforward since the file itself or anything else can take up some more space. So like Microsoft Word documents have their own headers and other information built in. And then if you add formatting to it, then it'll add even more to the file size. And so if we look at computer sizes, sorry, I'm going to zoom in a little bit here. Sizes are calculated as either powers of 2 or powers of 10. And the powers of 2 are whatever the prefix is, and then B bytes. So it'd be kibi bytes, mebi bytes, jibi bytes. And then the powers of 10, which we use much more frequently, are, I call them regular bytes. And they're such like kilobytes, megabytes, or gigabytes. And the important part is that the first 2 letters are the same. It's sort of how you can keep track without needing to know the actual like sizes and differences. And this accounts for the difference between advertised size and actual size for the most part. So a hard drive might be advertised as 1 terabyte, but it only has 931 gigabytes of usable storage because they're using one metric in the advertisement and then the other one on the actual measuring of things. And so I struggled for far too long with ggplot to try and find a way to like show the differences, but because some of the higher numbers get so large and the differences are so small, I ended up just using a dashed line, and you can kind of maybe see that the purple line starts going ever so slightly above the green line. Oh, and my key seems to have disappeared. Sorry, guys. There it is. Okay, cool. The salmon pinkish line is just the difference between the two. And the difference does appear to be getting larger, but again, yottabytes are like 2 to the 80. So it's a big difference, but it's also not really, because the numbers are so incomprehensibly large that it doesn't mean much. But zoom back out a little bit. And so I actually, before we jump in, I was like, it might actually be helpful to know where on the computer all of these different parts go. And so this is my motherboard that I use and my computer that I'm calling all of you on. And so over here, we've just got the spot where the CPU goes, and I'll talk about what all of these red letters mean soon, but we've got our RAM over here. We got some PCIe slots, 1, 2, 3, and then there's a smaller one here. We got some M.2 slots as well, and some SATA slots. And so just sort of, these are all on the motherboard, and that's sort of like the skeleton for your computer. So the CPU is kind of like the computer's brain. It gets a little bit more complicated at like the motherboard level, but it is just placed directly on the motherboard. And then clock speed is measured in hertz. Back in Stone Ages, everything was measured in regular hertz, or at one point they got up to megahertz, and now we're on to gigahertz. And we'll be there for a little bit, since most computers are sitting between like 3 and 5 gigahertz. And we'd have to go pretty high up to get to terahertz. And if we were to think of CPUs sort of as a coffee shop, each CPU can have many cores, and then each core can have 1 or 2 threads. And so that's sort of like the ability to multitask. So if our CPU was a coffee shop, each espresso machine that a barista can use is 1 core. And then if we add another barista to work on the same machine, it's like adding another thread. And so we can, by adding more machines or more baristas, we can speed up processes a lot. But adding another person to each machine decreases downtime a little bit, but the 2 baristas can get in each other's way. And so it won't be a perfect scale on getting faster. And the optimal number of cores or threads for a given operation can depend on what the operation is. Floating point operations, I believe, have many fewer benefits from using multiple threads, but they'll still benefit from multiple cores. And in R, that would be like using future apply or for or any of do parallel for each or any of the other multi-threaded or multi-cored operations. And then for the deep dive, some computers can have 2 or 4 CPUs. And again, we're hitting powers of 2. So most have 2 to the 0, which is 1 CPU. Some have 2 to the 1 for 2, or 2 squared for 4. All of the CPUs have to be identical. You can't mix and match. And then practically this adds more cores and threads. Once you get into like crazy data center stuff, then it has some more differences. But most consumer computers have 6 to 24 cores, with some up to 64. And I know lately Intel has sort of been splitting it where they'll have some sort of like high power cores and then others that are a little bit more power efficient, so that if you've got something crazy you need to do, the chipset will automatically assign the more intense operations to the high power cores. And then server CPUs tend to have more cores. That's a common theme. Servers are bigger, and those go up to 96 cores usually, but those also will require special RAM. And there's nothing preventing an enterprising consumer from buying a server CPU if they wanted to. I guess sometimes it can be cost prohibitive, but you can. And historically, there have been sort of like 2 big consumer hardware CPU manufacturers. And so AMD have usually had offerings with more cores, but Intel seems to get better single-threaded benchmarks than AMD. And so some people will choose which CPU brand they want based on if they'll be doing a lot of multi-threaded things or a lot of single-threaded. And so R usually is single-threaded, but again, you can always multi-thread. And then lately, the Apple M series processors have been sort of blowing Intel and AMD offerings out of the water on certain workflows, but moving over to Apple, you can't really configure the hardware as much as you might like to. And so your RAM is the random access memory, and it is memory that can be accessed randomly. So you only have to read the bytes that you need. You don't have to scan through any extra data to find the information you want. And RAM is really important in R because it loads all of your data into your RAM, and that can limit how much data you can work with, and running close to that limit can really slow things down, even if you're not hitting the limit directly. And the old rule of thumb was that your RAM should be 3 times larger than your largest data set that you're working with. I think that's one of those things that sort of like changes with the times, especially as we get better options for larger than memory like processes, so like Spark or Arrow, then you can start moving some things to your disk. But RAM can often be upgraded, and it's relatively inexpensive to do so. So if you can, you probably should. But increasingly, it's being soldered directly to the motherboard. And that's the big sort of Apple problem, I'll call it. That besides some of their, like, I think it's just the Mac Pro, but all of the rest of them, you get what you get and you don't get upset. And then same with a lot of other modern laptops as well. It just soldering it saves sort of like vertical space. And so in the race for the thinnest laptop, consumers lose. But we got some extra deep dive on the RAM too. And so we've got different generations that have to be matched up to your CPU and motherboard. But some CPUs and motherboards will support pairs of sequential generations. So a lot of the latest stuff coming out supports DDR4 and DDR5. And so there's even still new DDR4 stuff being released just because the newest RAM is actually significantly more expensive, partly, I think, due to the whole chip shortage fiasco that we've been living through for the past few years. But RAM also comes in different speeds inside each generation, and each generation will overlap a little bit. And the faster your RAM, the faster your data goes. You can work with your data. But again, it has to be matched to your CPU and motherboard. And if you're not careful, the fallback speed is generally the slowest speed of that generation. And so it will work. It just might not be as fast as you had hoped for. And then CPUs support and motherboards have a certain number of channels for RAM, which is, again, usually a power of 2. And it prefers to be installed in pairs split across channels. And so rather than having like one very long hallway or one very long one-sided hallway, you have a shorter hallway with doors on both sides. And the RAM in each channel should match, but different channels can be different. But again, it might slow down a little bit, but then you have to decide, is it worth it for the extra memory? And then servers require special RAM, which can detect and correct in-memory data corruption. So that's really important if you're doing high precision work, then you want to make sure that some random entropic little like thing doesn't mess up your data. But for the RAM channels, it's kind of confusing. So on this motherboard picture, I don't know if you guys can see it, but it says like A1, A2, B1, and B2. And so you would want to fill first, I believe. Looking at my own, it looks like I filled A2 and B2 first as my first pair, and then my second pair was A1 and B1. So then if we hop over to storage, just like the save button is a floppy disk from days gone by, the term hard drive may refer to actual hard drives or solid state drives. And hard drives use spinning disks, frequently, many of them all packed together in sort of like a little stack. And then solid state drives use magic. I tried finding like a good explanation that made sense that I could give you guys, but the best I had was you have a certain amount of voltage applied or removed from each memory cell. And there's something about the controller that lets you access each of those relatively quickly and without having to scan across a large swath like hard drive disks do. And for the time being, hard drives provide more storage at lower cost than solid state drives, but they're usually much slower. And just raw storage capacity isn't as important to R since you load data into memory, but it can still impact import and export workflows. And write speeds are usually slower than read speeds. So if you're writing out a lot of data for whatever task, then it's something to be aware of. And similarly to RAM, running close to full can cause general slowness because you'll have any sort of swap or just like extra cached data from either your operating system or any random process that will take up and fill that available space. So hard drives, as slow as they are, they're still very important. And they're generally measured in how fast, in size, and also how fast their platters, which is that disk where the data is stored, how fast they spin. Most consumer ones are 5,400 or 7,200 rotations per minute, with some enterprise drives going up to 15,000. And these read usually around 80 to 160 megabytes per second, which is solid, but it is, we'll see, slower than solid states. And this is where things get fun. So hard drives were traditionally made with conventional magnetic recording, where the read and write track are the same width. So on your disk, there's a sort of like a little arm, like a record player, and that will read or write data to the specific hard drive platter. And then some hard drives are now being made that use shingled magnetic recording, where the read track is narrower than the write track. And this allows data to be more densely packed, since parts of what's written can be safely overwritten without data loss. But the write speeds at first are similar to the conventional drives, but it degrades a lot when you run out of cache space. And these drives are usually less expensive. And so if you have some workflow that requires writing a large amount of data, then accidentally purchasing a shingled magnetic drive would really slow things down, essentially to a crawl. And manufacturers publish whether or not a hard drive is conventional or shingled, but they're really not happy about it, and they'll hide it. And then some drives will also come in both versions, and the only difference is the part number. So it's really tricky to keep track of, but for reading, it's fine. But if you're writing a lot of data, then it's just something to be aware of. And solid state drives are equally confusing, but in different aspects, because speed can be dependent on roughly 3 different things. So the connector and the generation of the connector, because newer generations are usually faster. The form factor does not always correlate to the connector type either, which is unfortunate. We also have a storage type and storage layers. And I found this really neat graphic that sort of shows out a little matrix of the different shapes and connectors, protocols, technologies, and form factors. And so your sort of traditional, the 2.5-inch drive, early laptops had 2.5-inch hard drives rather than the older 5.25-inch, I believe, like the really big blocky ones. But these are usually SATA. And then U.2 is very similar, but it uses a much faster connection protocol and storage technology. M.2 gets confusing because the connector, the SATA connector is also, it's a protocol and a form factor. And here the M.2 connector is using the SATA protocol. And then you can also have a faster protocol with PCIe that uses NVMe technology, or you can just plug it straight into a PCIe lane with NVMe. So again, very confusing, but I guess I should have mentioned it sooner. There's a great website called PC Part Picker that if you're trying to build a computer or figure out if things work together, it is crowdsourced, so you do always want to double check, but it will yell at you if things aren't compatible with each other, which is great. But so the connector can be SATA 3 nowadays, but again, you can also have an M.2 form factor, and this regular one is what's used by most hard drives nowadays and tops out around 600 megabytes per second. And so if we remember our hard drive speeds, that's considerably faster than a single hard drive. PCIe, which is if you game at all and you have a graphics card, it's actually the same protocol. And the 3 latest generations top out at wildly different speeds, just under 1,000 megabytes per second, 2,000, and then 12,000 for generations 3, 4, and 5. And then I believe generation 6 is being worked on currently. And then we've got the storage type, which is SATA or NVMe. And this one generally works with PCIe lanes, while SATA storage type works with SATA connectors and lanes. And then if you guys remember that when I said solid state drives are magic and there's a certain voltage applied to or removed from each cell, and I also said that computers are binary and they're either on or off, well, guess what? Not anymore. Some solid state drives use different numbers of layers of voltage. And so there's single, multi, triple, and quad level. And that essentially takes, instead of saying 0 and 1, multi-layer will say 0.5 or 1. And then triple layer will do 0, 1/3, 2/3, and 1. And more layers means slower, more unreliable drives because that difference in voltage between one level and the next starts decreasing. Higher layer counts are less expensive, but again, they have lower drive lifetimes and they're a little bit slower. And like with the conventional and shingled magnetic recording, manufacturers do publish this information, but they're not happy about it, and they will usually try and hide it. So it can be difficult to figure out. And so sort of a final overarching storage deep dive is that you can mix solid state drives and hard drives to meet user needs. So I know when solid state drives first came out, a lot of people who played a lot of games would put their games on a solid state drive and then the rest of their storage on a hard drive. And that helped. The games were faster, and then if they're writing a Word document, it doesn't matter if it's not fast. If you're using larger than memory data, you can use RAID. There's a few different implementations, but that allows you to use multiple identical storage devices that act as one device. And so if you took 2 identical hard drives and you mirrored it, then your write speeds would be slower because you have to write to 2 drives. But if you're reading, you can read from 2 drives at the same time, and that will speed up your read a lot. You can also stripe it, which will increase your write speeds, because you're now writing, if I had to write out the numbers 1, 2, 3, 4, I could write 1 and 2 to one drive, and then 3 and 4 to another. And so I can write twice as fast. And then some implementations will also allow for extra parity disks to protect against data loss. So now that if you only have half your data on each drive, you could add a 3rd drive or more. That sort of, it's some hashing algorithm that it'll use to check and say, hey, this 3 on this drive is missing. I can fill that in. Apparently I started a sentence. Beats me. Oh, I probably was going to say you can also mix and match mirroring and striping. So if I had a set of 2 drives that I striped and then another identical set of striped drives, I could mirror them. But then once you start adding drives, the only big thing that happens is your write speeds get slower, but your read speeds can increase a little bit, because again, you have to write out to all of those drives at some point or another. And this can also help protect against data loss. I mean, it kind of makes sense if you're writing to 2 hard drives at the same time. If one fails, you still have the other one. With 32 and 64-bit systems, things get a little funky, but we can sort of forget about the CPU, RAM, and hard drive craziness for a bit. R used to come in 32 and 64-bit versions. The last version to do both, I believe, is 4.1.3. And 32-bit systems, because they can't handle big enough numbers, essentially, they're limited to using 4 gigabytes of RAM. And that in turn limits R roughly to about 3 gigs. And so if you have data that's larger than 3 gigabytes, you probably want to use 64-bit. And I believe the book said some systems go up to either, it's like 64 or 128 terabyte limit on RAM. But some database connections do require 32-bit R if they're older. But you can pretend that 32 and 64-bit R get along by using a system call to 32-bit R to run just the bits you need, and then pass the data between 32 and 64-bit R by writing to data files of your choosing. And this is where trying to optimize your hard drive or solid state drive can help a lot. And this is, of course, not ideal, but some of those database connections are very old and unlikely to ever be updated to 64 bits. So a quick final note on networking: if you're pushing or pulling large amounts, so reading or writing large amounts of data from a network drive or a server or the internet or anything over a network, your networking infrastructure could need some upgrades if it's slowing things down, but that's a totally different chapter that's not in this book. But a quick overview: Ethernet is almost always faster and more reliable than Wi-Fi. So cables are faster than wireless. Makes sense. Ethernet rated for 1 gigabit per second usually maxes around 125 megabytes per second, which, if you remember our chat about hard drives, is well within the range where you could max out the hard drive's write speed before you're maxing out your network. And then that 125 megabytes per second is actually the same as 1,000 megabits. Again, the numbers start getting confusing because they're in slightly different bases and powers. Some companies have been upgrading to 10 gigabit networks, and then of course data centers can go higher. And I believe that's one of those things where they essentially just take a bunch of tiny cables, pack them into one really large cable housing, and then go, look, I made a faster cable. And it's like, no, you just made 1,000 regular speed cables, but it works. So not, yeah. But you don't have to worry about most of this if you switch to cloud computing. You can configure the server almost exactly how you want it, but here you do have to be mindful of costs, where if you're building your own computer or a workplace is providing one, it's sort of a one-time cost plus any maintenance, which is usually pretty rare, and electricity costs, whereas using cloud computing servers are ongoing smaller costs. And the DevOps for Data Science Book Club talks about cloud computing a bit more, and Cohort 1, I guess, has mildly, we've soft ended, but you could help start Cohort 2 if you want to learn more. So that is the efficient hardware chapter. Again, it's not necessarily something you would worry about at work unless they specifically say, hey, you can build your own computer. And then I promise it's not as hard as it sounds. It's basically just Lego for grown-ups. It is a lot of fun. And if you have the opportunity to do so, I do recommend it.
Very nice.
Yeah.
Have you, or has anyone run into the 32-bit database issue? You have? Is there a general category, how much info can you tell us about how and when?
I mean, I don't remember which databases it was. I think there were some like the classic, we have a mission critical access database that you can't touch. And then I think that was most of it, was just like those random access databases. And then for a little bit, it just took time for IT to sort of find the new drivers that they wanted to use. But of course, that always lags behind. But doing this switch back and forth is the best way, I guess, to do it. Would be you create a .r file, make sure all of your stuff is set up in 32-bit with like your whatever libraries you need. And then you just switch back over to 64, and you can use system to just run a source command on that whole file. And then you write it out to whatever. I think at work we usually did CSV files, but I know one of my coworkers he was stuck in 32-bit for whatever reason, had much larger than memory data, and ended up having to use an awk command to read the CSV and filter it before loading it into R, because all of the R methods would try and load the file first, or were so slow that it wasn't really like time efficient. So he ended up using it was the Windows subsystem to filter and then read it in bit by bit. Not bit by bit in like the computing sense, but chunk by chunk. So
fun.
No. That's
all right.
all right.
Anyone have any other thoughts, questions? Before we go, oops, let me pull up the spreadsheet. And I think, Melanie is going next week. You're still on for that? Okay. And I still didn't contact Quinte Kim to see if he's going to be around for chapter 10, but I'm assuming not, and I will probably just take that. Cool. All right.
Was very interesting. Thanks.
Yeah. Thank you very much, Gus. I'm glad we found something that you could geek out on.
Yeah, no, it was a scheduling thing for a bit, and then hardware, I just was like, oh, I know a little bit about hardware. So
All right. Thank you.
happy to oblige.
All right. All right. Bye.